state of New Jersey. And she has done quite a bit in the chemistry department. She has worked for me for a summer. She has been very active as a tutor. She sat in on my organic class again this year to really help my students out, and she's been a fantastic contributor to our program. She has had a pretty long-standing relationship with the University of Nebraska. I think she, going out there for a visitation, doing summer research there last summer, and now she's going to, I guess Lincoln must be a cool place, because she's going to can take the next step of her journey there, and she's going to try and push into materials chemistry, where she'll take her kind of experience of thinking about the world at a molecular level and just kind of broaden that out a little bit to think about surfaces, think about materials and surfaces at the atomic level. So it's an exciting jump, and I'm excited to hear about the work she did last summer in Lincoln. So take it away.
Thank you so much, Stefan, for that introduction. And good afternoon, everybody, and thank you for tuning into my talk via Zoom, Deuterated Diisopropylammonium Bromide, Structural Studies of an Organic Ferroelectric. My name is Winnie, and today I will be talking about the research I did this summer at an REU at University of Nebraska-Lincoln's Materials Research Science and Engineering Center, affectionately known as the MRSEC. With Dr. Stephen Ducharme as my principal investigator, I researched about the effects of deuteration on the known organic ferroelectric material, diisopropylammonium bromide, and today I will talk to you about the synthesis and characterization journey that this research took me on. Just as a note, for the rest of the talk, diisopropylammonium bromide will be referred to as diisopromide, and deuterated diisopropylammonium bromide will be referred to as deuterated diisopromide. Now, without further ado, let's dive into the wonderful world of ferroelectricity. The first thing today we are going to talk about is background information. This includes why we care about ferroelectrics, what they are, and why we are interested in deuteration, which is when you add heavy hydrogens to a compound. Once we are done with background information, we will then go and talk about the methods. I will talk to you about making my target compound, growing my compound as crystals, and characterization, which is examining the properties of my target compound. I will then talk about my conclusions. I had 5 main conclusions from this research, and we will go over each one of them and their implications. Finally, we will talk about future studies and which ones may be applicable for this research. Organic ferroelectrics are a rapidly emerging field in the material sciences, and there are many directions that this research can take. Did you know that a camera's flash may use ferroelectric materials? This is because ferroelectric materials make great capacitors. Capacitors are able to hold electric charges on them, and because of this, are necessary for building both this and the next generation of electronics. Because ferroelectrics can hold charges, they are still being studied for use as capacitors and are being able to see if they are more effective than non-ferroelectric capacitors. Ferroelectrics are also being experimented on as ferroelectric random access memory, or FRAM, for a computer, which is a type of non-volatile random access memory. Compared to its competitor, dynamic random access memory, FRAM can be made less dense, consume less power, and complete writes more quickly. However, since it is still an emerging field, currently, FRAM is more expensive than the already established dynamic RAM. Before we dive into the specifics of my research, we must first understand what a ferroelectric material is. A ferroelectric material is a material that has a spontaneous, nonlinear, reversible polarization. This means that the polarization is able to switch back and forth in the presence of an external electric field. It is important to note that the flipping of polarity happens in the presence of an external electric field, as it can't happen without the electric field. This flipping of polarity is a key hallmark to ferroelectric materials and is why they are such good capacitors. This flipping of polarity can be visualized by this hysteresis loop. When an electrical current is passed through a ferroelectric material, it will create a hysteresis loop, which is why the polarity is considered nonlinear. The polarity at the top and the bottom are flipped, and the x-intercepts is where the flipping of the polarity actually happens. It is due to this polarity flip that ferroelectrics are good at storing charges as a capacitor, and why they are being looked at as an alternative to traditional memory devices that we discussed in the prior slide. Ferroelectric materials are also considered piezoelectric materials. A piezoelectric material is a material that creates a temporary voltage upon mechanical stress. Applications of the piezoelectric material include an electric cigarette lighter, like the ones you might have in a car, a record player needle, sensors, and piezoelectric motors. The triangular diagram shown here shows that there are many interactions that happen in the thermal, mechanical, and electrical properties of a crystal. The line shows that a change, even a very small change, in one variable will produce a corresponding change in its linked variable. In this case, a change in constant stress will create a change in electrical displacement, which is what causes the temporary voltage. Because ferroelectrics are piezoelectric, ferroelectric materials are being looked at in these applications as well. Scientists are looking at whether their piezoelectric effect, along with them being good capacitors, can create new generations of electronic devices and motors. If you can recall, my research isn't just about ferroelectrics, but about the emerging field of organic ferroelectrics. Why would we use organic ferroelectrics in comparison to regular non-organic ferroelectrics? Non-organic ferroelectrics are often made of toxic materials or heavy metals, such as lead, in the case of lead zirconate titanate, and are often expensive to produce. In comparison, organic ferroelectrics are made up of materials that are less toxic to both humans and the environment, and once they are further researched, are anticipated to be cheaper to produce than non-organic ferroelectrics. So now that we know about why we would choose to use organic ferroelectrics in comparison to non-organic ferroelectrics, what exactly are organic ferroelectrics? Simply put, organic ferroelectrics have the same properties of non-organic ferroelectrics, but are made of organic compounds. Organic compounds are compounds that contain carbon and hydrogen. So organic ferroelectrics are piezoelectric compounds that have a flippable polarization. They can come in either solid or liquid crystalline structures. An important thing about organic ferroelectrics, or ferroelectrics in general, is their Curie temperature, or T sub C. Before heating, these crystals do not have any ferroelectric properties and are non-polar. This makes sense because they do not have that flippable polarization yet that is required of ferroelectrics. However, when heated to Curie temperature 1, they become ferroelectric. An amazing thing is that they do not have to remain at this temperature to be ferroelectric, only that they are heated to the temperature once. Due to the charge centers being changed while heating, they emerge from the heating as a ferroelectric crystal, complete with the spontaneous flippable polarization. Upon reaching Curie temperature 2, they are then paraelectric, which is a material that has a nonlinear polarization, but the polarization graph is not shaped like a hysteresis loop. Organic ferroelectrics demonstrate versatility and have a great potential for use as a replacement for regular non-organic ferroelectrics. As I said, scientists are extremely interested with organic ferroelectrics due to their non-toxicity and cheaper production costs. A particular compound of interest is the Diisopropylammonium, or DIPA compound. The reason this compound was of interest is because scientists thought that when paired with a negative ion, the DIPA compound could be potentially ferroelectric. So, 3 different DIPA X compounds were tested, with X being 3 different halogen ions from the periodic table: chloride, bromide, and iodide. These 3 different compounds that they tested were DIPA chloride, DIPA bromide, and DIPA iodide, with halogens being of interest because DIPA chloride was discovered to be ferroelectric. In the research I did, DIPA bromide is being studied because it was a confirmed ferroelectric, has less studies done than DIPA more ferroelectric potential, and is less problematic than DIPA iodide, since there are many disagreeing sets of data that deal with DIPA iodide, such as disagreeing phase transition temperatures and melting points. The picture shows a cross-section of the ferroelectric crystal DIPA bromide. Isopropyl groups are ignored and dotted lines are the hydrogen bonds. The hydrogen bonds are the most important part of the diagram, so I enlarged this part of the graph to the structural scale. As you can see, the NH2 acts as a hydrogen bond donor, and the bromide ion acts as a hydrogen bond acceptor. Now, remember when I said that the crystal goes from a non-polar, non-ferroelectric phase to a ferroelectric phase by heating? Well, scientists are not quite sure the mechanism as to how the crystal goes from being non-ferroelectric to ferroelectric, but they have a hunch that the major contributing thing are the hydrogen bonds, which are shown as dashed lines. In order to probe into the hydrogen bond, deuteration studies are used to shed light into the dynamics of the phase transition. Deuteration has helped understand the phase transition in other ferroelectric materials, such as potassium hydrogen phosphate. When potassium hydrogen phosphate was deuterated, the phase transition temperature jumped up about 100 degrees Celsius, so there was evidence that deuteration did affect the phase transition temperature in some way. We are hopeful that deuteration will help us understand the phase transition of diisopromide. Isotopes are multiple forms or versions of an element. Each element has the same amount of protons. Changing this would change the element itself, but different amounts of neutrons. Since there are different amounts of neutrons, different isotopes of the same atom weigh differently from each other. Hydrogen has a few different isotopes, but we are interested in deuterium, which is a specific isotope of hydrogen. The reason we are interested in deuterium is because A, it is relatively easy to obtain in things like D2O or heavy water, and B, because it will affect the hydrogen bonding. An ND2 bond is tighter than an NH bond and is less likely to hydrogen bond. In playing with these hydrogen bonds, we are hopeful to see if the transition temperature that the compound has will be affected. In the diisopromide molecule, there are 16 hydrogens, but the amine group hydrogens are the ones we want to deuterate. This is because the amine group hydrogens are the hydrogens involved in the hydrogen bond that we want to dig deeper with, because it may be responsible for the phase transition. The synthesis of diisopromide was rather simple, and you will see very quickly that this was not a synthesis project. Hydrobromic acid was obtained and put in a burette in preparation for a dropwise addition. Then commercially available DIPA was obtained and put in a beaker. The hydrobromic acid was added dropwise to the beaker of DIPA in a 1-to-1 molar ratio. The reason the hydrobromic acid was added dropwise was to avoid excess heat buildup and the formation of unwanted side products. The less side products we had, the less we would have to take time and purify the product. However, just in case, the crystals were purified by recrystallization in methanol, with hopes that the impurities would remain in the methanol and only pure diisopromide would recrystallize out. The newly formed product was then characterized in order to make sure that what we had was in fact diisopromide, and it was in fact diisopromide. In order to deuterate our new diisopromide, the crystals were soaked in heavy water or D2O until it started to form crystals, new crystals. However, this process must be done in a glove box with an inert atmosphere. We use nitrogen. For all you people who have used a glove box and know that water typically doesn't go into a glove box, don't worry, we had a dedicated glove box for this purpose only. The reason it had to be done in a glove box is to minimize the hydrogen-deuterium exchange. Summers in Nebraska can be surprisingly humid, which means that the air has water in it. The hydrogens in water could potentially swap themselves with the deuteriums in the heavy water and render the deuteration process useless, since the crystals could emerge partially, if at all, deuterated. Once the recrystallization process was finished, the resulting product was deuterated diisopromide, presenting itself in thin, needle-like crystals. Now we are going to talk about nuclear magnetic resonance, or NMR. NMR is a technique used to determine the structure of compounds and is a powerful analytical instrument. With this research, NMR is going to be used to see if the diisopromide has been successfully deuterated and to the extent it has been deuterated. Now, before I show you the NMR spectra for the deuterated diisopromide looks like, let's have a little conversation about NMR, more specifically Proton Nmr. Spinning nuclei act like little bar magnets, and when they spin, they create a magnetic field. When undisturbed, the nuclei are oriented randomly and the poles of the magnet, quote unquote, point in all directions. However, in the presence of a magnetic field, their orientation flips to align with the external magnetic field, pointed either up, alpha, or down, beta. Inside an NMR, there is a large magnet that creates a large magnetic field, usually from about 1 to 20 Tesla. In the presence of this strong magnetic field, the nuclei in the sample align in either alpha or beta position. A radio frequency from a radio frequency transmitter is applied to the nuclei and flips the nuclei from alpha to beta position, which is low to high energy orientation. As the nuclei flip back from beta to alpha, this creates a little bit of current within the receiver coil due to the nuclei being a magnetic field. A signal is produced, and after a Fourier transformation, an NMR spectrum is produced. Reading an NMR graph can give you much information. Each peak represents a unique hydrogen, and by integrating or finding the area under the peak, we can see the relative amounts of hydrogens there are, chemical shifts, and the splitting of the peaks is caused by how many immediate neighbors each hydrogen has on the molecule. So now that the synthetic process is over, I now had to see if what I had is actually deuterated diprobromide. In order to do this, I used Nmr spectroscopy. This is the full Nmr spectrum of deuterated diprobromide and non-deuterated diprobromide for comparison, but it's a little hard to see, so it's so small. So let's zoom in on the most important peaks. I am going to draw your attention to the leftmost peak circled here. This is the amine peak created by the signal that the amine or the ND2 group gives off. Remember, it is the amines that we want deuterated since the amines are part of the compound involved in the hydrogen bonding, which could be a key to understanding the mechanism of ferroelectricity. Since the compound is deuterated, we would expect the amine peak to be significantly decreased in comparison to the non-deuterated diprobromide spectra, since there would be deuteriums instead of hydrogens on the amines, and deuteriums don't give off a signal in proton NMR. And lo and behold, when compared to, yes?
I think you should kind of back up because this is an important slide and you went out.
Oh, did the connection go out? Okay. I will back up. Okay. Can everyone hear me? Okay. So now that the synthetic process is over, I now had to see if what I had is actually deuterated diprobromide. In order to do this, I used Nmr spectroscopy. This is the full Nmr spectrum of deuterated diprobromide with the Nmr spectra of diprobromide in there, just for comparison. It's a little hard to see, however, because it's so small, so let's zoom in on the important peaks. I am going to draw your attention to the leftmost peak, circled here. This is the amine peak, created by the signal that the amine, or the ND2 group, gives off. Remember, it is the amines that we want deuterated since the amines are a part of the compound involved in the hydrogen bonding, which could be a key to understanding the mechanism of ferroelectricity. Since the compound is deuterated, we would expect the amine peak to be significantly decreased in comparison to the non-deuterated diprobromide spectra, since there would be deuteriums instead of hydrogens on the amine, and deuteriums don't give off a signal in proton NMR. And lo and behold, when compared to the non-deuterated diprobromide spectra, there is a significant decrease in the amine peak, suggesting that deuteration was successful. This leads to the conclusion that the amine protons are deuterated, while the rest of the compound was left largely unchanged. This also shows that the compound prefers to have the amines deuterated, since the deuterium-hydrogen exchange was at a minimum. If the amines did not prefer to be deuterated, then the deuterium-hydrogen exchange would have been more of a problem, and we probably would have not seen deuterations to the extent that we saw. Next, we will talk about a technique used to grow crystals and create high-quality microcrystal arrays, lithographically controlled wetting. This is a technique that is used to grow crystals in neat, orderly rows on a substrate or surface. The reason we would want neat bands of crystals on the substrate is because if the substrate with crystals on it were to ever undergo electrical testing, the crystals would need to be in neat bands in order for the electrical current to pass uninterrupted through the crystals. So now that I know that I have what I want, I can start growing crystals on doped silicon substrate using the lithographically controlled wetting technique, or LCW for short. LCW allows crystals to be grown in a consistent, ordered fashion on a substrate, which is important because if they need to be in neat, orderly rows if I ever wanted them to undergo electrical testing. First, I start with a drop of deuterated diprobromide on doped silicon substrate. LCW employs the use of a PDMS, which is a type of silicon mold. Think of silicon molds that you might have in your kitchen. It has imprints on it made from the tiny grooves from the front side of a DVD. This PDMS mold is then placed over the solution of deuterated diprobromide on the substrate, and as the deuterated diprobromide recrystallizes, adhesion and capillary action forces the solution to recrystallize while still touching the grooves of the PDMS stamp. When the recrystallization process is complete and the stamp is pulled off, what remains are crystals grown in a consistent and orderly fashion. In order to grow the best possible crystals for future testing, I optimized the parameter for growth with respect to concentration and drop size. For concentration, 3 concentrations of deuterated diprobromide and D2O were tested. 5 grams per liter on the left, 10 grams per liter in the middle, and 20 grams per liter on the right. By looking at the growth with a scanning laser microscope, I can see that the 10 grams per liter gave the most ideal crystal growth. 5 grams per liter was spotty growth in places, and 20 grams per liter was often overgrown, completely bypassing the grooves from the PDMS stamp and instead growing in thick sheets across the substrate. Once the concentration was optimized, I tested the drop size using the 10 grams per liter concentration. Since the syringe we used to drop solution onto a substrate was in a 100 microliter syringe, I tested 3 drop sizes, 5 microliters on the left, 10 microliters on the middle, and 20 microliters on the right. The reason I didn't test drop sizes greater than 20 microliters was because those drops would be so large that they would run off the substrate once the PDMS stamp was pushed down onto them. Again, after imaging with a scanning laser microscope, it seems that 10 microliters was the most ideal drop size, since 5 microliters produced inconsistent growth and 20 microliters was overgrown in places. Although some substrates showed under and overgrowth in all concentration, after repeating this test many times, it seems that 10 grams per liter and 10 microliters were the parameters that caused the most consistent crystal growth. So overall, the most ideal conditions to produce a good crystal growth were 10 grams per liter and 10 microliters. This is important because the crystals need to be in neat, orderly rows in order to have the best chance of success for electrical testing. The electric current would need to be run through the crystals on the doped silicon substrate, and this would not be as successful if the crystals had patchy growth or were overgrown. The next characterization technique in this talk is powder X-ray diffraction. There are 2 types of X-ray diffraction, single crystal and powder, but the instrument I used was the powder X-ray diffraction instrument because for us, it was easier to grind the crystals into a powder than to try to grow a single crystal for analysis. There are 2 structures that the deuterated Diisopropylammonium crystals have been shown to grow in. The X-ray diffraction will allow us to see which structure the deuterated Diisopropylammonium crystals are in. This is important because one structure has ferroelectric properties while the other structure does not. Before we get into my X-ray diffraction spectrum, I will take you on a quick crash course as to how an X-ray diffraction instrument works. The reason you use X-rays is because you want to interact with inner core electrons, and you need high energy X-rays in order to be able to interact with these inner core electrons. X-rays are shot through a sample, which is mounted and rotated on a sample holder. The powder sample then causes the X-rays to diffract in a certain pattern. The pattern of diffraction is unique to the structure that the crystal grew in and can be compared to a quote-unquote fingerprint. An example of an X-ray diffraction spectra is shown here. Both of these spectrum are calcium carbonate or chalk. However, calcium carbonate can take on 2 different crystal structures. In order to know which of the 2 different crystal structures the chalk grew in, you do not need to identify each peak, only the pattern of the X-ray diffraction spectrum. Now that we have the powder from the deuterated Diisopropylammonium crystals, we need to see what structure they grew in. X-ray diffraction can be used to see how the crystal grew in and what structure it grew in, since crystal structures will have unique X-ray diffraction spectra. Deuterated Diisopropylammonium can grow in 2 structures, monoclinic and orthorhombic. The differences between these 2 structures lie within the unit cell of the crystal, but the important thing to note is that monoclinic crystals are the only structure in which ferroelectric properties are present. The spectra of the monoclinic, ferroelectric, and the orthorhombic crystals look different, so through X-ray diffraction, we will be able to pinpoint which structure the crystals are in. Before X-ray diffraction measurement, we scraped all the crystals off of the LCW surface and heated them. Why heating? Remember, the crystals need to be heated in order to exhibit ferroelectric properties and that they don't just spontaneously grow as ferroelectric crystals. The phase transition temperature for deuterated Diisopropylammonium seems to be around 160 degrees Celsius, so we heated the crystals to 160 degrees Celsius. A heated sample of deuterated Diisopropylammonium gives a shifted monoclinic structure, and the peaks around 16 degrees and the evenly spaced triplet around 22 degrees are telltale signs that the heated deuterated Diisopropylammonium crystal is in the monoclinic structure, since these features are on the same on X-ray diffraction graphs of ferroelectric non-deuterated Diisopropylammonium crystals. Although the scanning laser microscope allowed us to see preliminary hope that the crystals grew in an orderly fashion, the crystals were still too small to get meaningful topological data off of them. So, once I had grown good crystal arrays on the substrate, I used atomic force microscopy, or AFM, to image the substrate and get some topological data on the crystals. AFM is a powerful, non-destructive way to analyze topological profiles of a sample. The reason we want the topological profile of the sample is because we want to see if the crystals grew in neat, orderly bands across the substrate or surface. The way an AFM works is that there is a small tip on the end of an arm. When the arm is brought within a nanometer's distance between the sample, it is deflected due to forces from both the tip and the sample. An atomic beam is used in order to get the best resolution you can. The deflection is then used to gather topological data about the sample. The output of the AFM will give you a picture and a graph. The image is my real-time image of the crystals with shading for contour. The shading will be able to show you at which points the crystals are taller or shorter. The graph is just a graphical interpretation of the image and will clearly show you the topological profile of the sample. It also allows you to pull numerical data, telling you how tall and wide your crystals are. Upon first glance, the crystals on the substrate look evenly spaced, with a consistent and orderly growth thanks to the LCW technique. When topological data is pulled, it only confirms this. The graph shows that the crystals in this swatch are approximately the same height and spacing apart. The crystals are approximately 138 nanometers tall and 1 micron wide. This is an important step in the research as it shows that deuterated Diisopropylammonium can be grown using the LCW technique and produce a sample that has crystals grown in neat, orderly bands across the substrate. There are 5 main conclusions to this work. 1, it is possible to successfully deuterate Diisopropylammonium at the amine site without deuterating the rest of the compound, as confirmed by Nmr Spectra. This shows that the amines prefer to be deuterated, while the rest of the compound does not. 2, deuterated Diisopropylammonium does not have significant structural differences from its non-deuterated counterpart. Both present themselves as a needle-like whitish clearish crystal, and both have similar chemical spectra. The Nmr and X-ray diffraction spectra were compared to the X-ray diffraction spectra of the non-deuterated Diisopropylammonium, and aside from the decrease in the amine, or ND2 peak of the Nmr, which is to be expected since deuteriums don't give off a signal in Proton Nmr, the remaining parts of the spectra are unchanged. 3, deuterated Diisopropylammonium can be heated into the monoclinic structure, just like Diisopropylammonium can. This is especially important because of deuterated Diisopropylammonium being able to exist in the monoclinic structure, more extensive tests can be done on it to see if it is in fact a ferroelectric crystal. 4, deuterated Diisopropylammonium can be grown using the LCW technique, and this growth is optimized, as visuals from the scanning laser microscope told us. The 5th and final conclusion is that atomic force microscopy proves that the LCW technique creates good crystal growth that happens in neat, orderly bands. This is important because if the deuterated Diisopropylammonium crystals on the substrate, they need to be in neat, orderly rows in order for the current to pass through the crystals. From this research, it seems that deuterated Diisopropylammonium is structurally the same as its non-deuterated counterpart, and that information from the deuteration studies can be applicable to studies on the non-deuterated counterpart. Remember in the beginning of this presentation when I talked about how ferroelectrics have a flippable polarization, and that this flippable polarization can be visualized by a hysteresis loop? Well, in order to 100% prove that the material is ferroelectric, we need to produce a hysteresis loop. People will want to see that the material can produce this hysteresis loop in order to accept that the material is ferroelectric. So the first thing to do for future work would be to confirm ferroelectricity and get a hysteresis loop by using what is known as a Sawyer-Tower circuit test. This is because even though the X-ray diffraction graph suggests that the material is monoclinic due to its unique pattern, the only way to 100% confirm ferroelectricity is to produce a viable hysteresis loop by using a Sawyer-Tower circuit test. A Sawyer-Tower circuit test employs a ceramic sample of the crystal. The crystal is turned into a ceramic sample by use of a hydraulic press, which creates high pressure. The disc is situated by electrodes, and an external electric field is run through the crystal. If the material is ferroelectric, it will have the characteristic hysteresis loop created by a material with a polarization that flips from positive to negative in the presence of an external electric field. Analyzing the results of this test is easy. If there is a hysteresis loop, the material is ferroelectric. If there is not, the material is something else, perhaps paraelectric, especially if we heated it too much. Another future test would be to use differential scanning calorimetry, or DSC, to pinpoint the exact phase or the exact temperature the phase transition happens at. The way it determines phase transitions is that there are two cells used, a sample cell and a reference cell. During a phase transition, more heat will need to flow to the sample cell rather than the reference cell in order to maintain both of them at the same temperature. A different amount of heat will flow to the sample and the reference cell during the sample's phase transition, and by observing the difference of heat absorbed by the sample and the reference, the amount of heat absorbed or released by the sample during its phase transition can be found. By plotting the data on a graph with heat released versus temperature, the exact temperature of the phase transition can be found. This is important because until this, we are estimating the phase transition temperature by experimental heating experiments. And with the data from the DSC, we would be able to get the exact phase transition temperature and always heat our crystals up to the exact temperature that it would become ferroelectric at, instead of heating it up to an approximate temperature and risking overheating. Remember that I said that ferroelectric materials have to reach the Curie temperature 1 in order to switch their ferroelectricity on? Well, currently the deuterated diisopropylammonium has an estimated Curie temperature of about 160 degrees Celsius. In other words, it needs to be heated up to about 160 degrees Celsius in order to exhibit ferroelectric properties. There are no known instances of crystals being grown in the ferroelectric phase spontaneously, and deuterated diisopropylammonium crystals currently must be heated in order for their ferroelectric properties to turn on. One future project would be to try and manipulate its Curie temperature. As of now, it is unclear as to how to proceed with doing this, but studies with pressure are being explored. What researchers are trying to do is put a non-ferroelectric crystal under various amounts of pressure, maybe even using a hydraulic press, to see if this can be responsible for triggering a switch from the orthorhombic to the monoclinic structure, thus changing the phase from a non-ferroelectric to ferroelectric. The more manipulation the Curie temperature can withstand, the more immediate industrial applications deuterated diisopropylammonium would have. So manipulating the Curie temperature is an important future step that this research could take. A final future project that this research could go towards is exploring the topological surface using piezo force microscopy, or PFM. A PFM works similarly to an AFM, except for the fact that there's a conducting tip that passes an alternating current through the ferroelectric material. A PFM works for any piezoelectric material, and remember that ferroelectric materials are also piezoelectric by nature. By creating contrast, ferroelectric regions of a material can be analyzed, meaning we can see which crystals on the substrate are ferroelectric. This way we can see if the whole substrate of crystals used for AFM analysis is all ferroelectric, if some of them are, or if none of them are. Since a PFM can also pass current through a sample, this would be a good way to see if the deuterated diisopropylammonium crystals can hold a current. The way to test this would be to grow deuterated diisopropylammonium crystals on doped substrate with electrodes embedded into it. Once the PFM would pass a current through the substrate, you could see that the deuterated diisopropylammonium crystals could hold that current until it was passed to the next electrode. This would be an interesting test, and the more the deuterated diisopropylammonium was able to hold a current, the more possible industrial applications it could possibly have, which would be cool for it to have, rather than it just being a study of phase transition mechanism. I would like to thank Dr. Stephen Ducharme for allowing me to learn and work in his lab, and the members of the Ducharme lab for being wonderful to work with. I would also like to thank the Lawrence University Chemistry Department for encouraging me to apply to this REU. I would like to thank Dr. Stefan Debert for being my on-campus advisor, both for the senior experience and for my academic career and life in general. I would like to thank Dr. Allison Fleshman for her valuable input for my project. I would also like to thank Dr. Deanna Donahue and Dr. Graham Sasma for teaching Chem 680 and for their input. This work was supported by the NSF through the Nebraska MRSEC. Additional characterization analysis was performed in part in the NSF, NNF, and CMN, and the NERCF at UNL. Chemical spectra were performed in part in the University of Nebraska-Lincoln Chemistry Research Instrumentation Facility. Finally, I would like to thank the Lawrence University Chemistry Department in its entirety for allowing me to learn from them for the past 4 years. I have left Lawrence as a better chemist in person. Here are my references. Thank you very much again for tuning into my talk, and I will be now happy to take questions.
Yay.
So I'm happy to Winnie's
I'll
happy
start
to-
off. So it seems like deuterated compounds, anything with a nitrogen deuterium bond, can exchange with water pretty quick, right? So
Yeah.
the effort that you made to
Stefan, we've lost you. I don't know if he's coming back. I guess, did somebody else have a question, or am I the only one who lost him?
No, I lost him too.
Okay. Stefan, where are you? Anybody else have a question? Nick, you're muted still. Nick. Maybe I can help. No.
Can you hear me?
Yes.
Okay. I was just wondering what kind of structural changes you were expecting to see with deuteration, like how precisely you would expect that to affect the hydrogen bonding.
We weren't really, am I muted? Am I muted or no? Okay, I'm good. We weren't really expecting to see structural changes with the chemical spectra because it is the same compound and deuteration just affects that hydrogen bond. We just needed to characterize the entire compound to see if there are any unexpected structural changes that we weren't aware of. As far as for the hydrogen bond, what would happen is that the phase what would happen is we give the data of the phase transitions, temperatures, and the both the deuteration and the undeutrated compound to a theoretical chemist and physicist, and then they, with knowledge that the hydrogen bond is probably the thing that affects the ferroelectricity, propose a model as to the dynamics of the ferroelectric emergence of the crystal. Does that kind of make sense?
Shall we give it another try, Stefan?
Are you answering my question, or did it entirely get cut off? I'm sorry.
Totally
I just
got
jumped
cut
back
off.
in. Yeah, all right. Yeah, I was just going to ask about hydrogen deuterium exchange once you've made the crystal, right? Do we have to worry about this taking water from ambient air and exchanging hydrogen with deuterium there?
No, it didn't seem like that happened. It seemed like the ND and I guess the NHs preferred to be deuterated because once the hydrogens came off of those and the deuteriums came on, whether we had the crystal just sitting in a fume hood in solid crystalline form for a couple days before taking the spectra, and it didn't seem that the spectra changed from when we took it immediately after the crystal formed.
Because you can see in your NMR, there is still a little bit of an NH peak there, right?
Yeah.
Like it's not 1, but it's not 0, and so
yeah, it's a baby.
Yeah. And so is there, and we could quantitate that if you wanted to. And is there kind of some percentage where you and your group decided that, okay, this percentage protonated is fine?
The percentage of the NMR graph that I showed you, I believe that was about 67% deuterated. The highest deuterated we got was about 80%, but through testing, the 67% seemed fine.
Okay.
Other questions? Evan?
Can you hear me?
Yes.
Sweet. 2 questions. Has there been any look into other counter ions other than bromine? Bromide, I mean.
Yes, as I mentioned earlier, DEPA chloride was found to be ferroelectric and extensive testing has been done on it. I think what they're doing now is working to actually find that mechanism as to how the ferroelectricity turns on and off. DEPA iodide is also being studied, except it's kind of shaky because there's many disagreeing sets of data about DEPA iodide. Things like melting point, things like phase transition temperatures, scientists are disagreeing on. So that's being studied further. And as far as other ions other than halogens, not yet, but that might be a thing for future testing to see if any other ions other than halogen ions can produce ferroelectric effects.
Okay, that's yeah. The only other question I really had was, so you looked at the the diisopropylamine. I was wondering if there was any insight into other like similar strong bases, maybe like bis trimethylsiloamide, amine. Geez, I'm sorry about that.
I haven't tested that yet, and all the literature I've read only tests the diisopropylamine system, but that might be a good thing for future testing to see if other structural skeletal things that have chemical properties similar to diisopropylamine would also have similar ferroelectric effects.
Thanks.
Other questions? Frankly.
I got a question about the ferroelectric thing. You said that once it's heated up once, then it's to go. So is it just like always okay? Like you heat it up once and for all the time, it's just going to be ferroelectric? Or is it like a degradation over time?
No, once you heat it up once, it is still ferroelectric, and that's because the heating physically changes the crystal from an orthorhombic structure to a monoclinic structure, and then once the crystal structure is changed, it doesn't go back.
Any other questions? Does not look like it, but if somebody I'm missing you, just speak up. Otherwise, I think we can thank Winnie one more time for giving us such an informative talk. Me clapping very loudly to get it from everybody. And I hope to see you guys at our next sessions. As I said, we will be hearing about 2 talks on Wednesday, and then 2 talks on Friday, and then even more the weeks after that. If you want to hang out and ask Winnie any questions, we will be here for a little bit longer. But otherwise, thank you all for attending, and I hope you have a wonderful day.